Good afternoon from Japan. Thank you very much for inviting me your lecture. My name is Hajime Yano from JAXA AiS. Today, I would like to talk about sensing technology in planetary exploration, especially cases for Hayabusa and Hayabusa 2. On the Earth, we still keep receiving extraterrestrial materials from the outer space, 4 plus minus 2 to 10 to the 4th metric ton per year, according to Love and Brownlee 1993, in the form of cosmic dust. Cosmic dust is regarded as a delivery vehicle of water and organics of the Earth. And this is a central theme of JAXA's small body exploration strategy. Especially meteoroids originated from comets and asteroids, and those are regarded as fossils of our solar system genesis, buried with heliocentric distances from the proto-sun, ranging asteroids in near sight to the comets and the Kuiper Belt object to the farther away. So therefore, we are now living era to bring samples from those the primitive bodies of the solar system, such as cometary nucleus and asteroids. So we have our so-called flyby sampling technique, such as stardust, and the rendezvous sampling technique, such as Hayabusa, Hayabusa 2, and now OSIRIS-REx for America. So for the rest of my talk, I would like to concentrate on Hayabusa and Hayabusa 2's rendezvous sampling technology. The first Hayabusa 1, or original Hayabusa, which was launched in 2003 and has returned to the Earth in 2010. It was defined as a first technology demonstration mission for asteroid sample return. And then we have Hayabusa 2, which is launched in 2014 and has returned to the Earth just a few months ago, last year, December. So after the success of the Hayabusa 1, the Hayabusa 2 is now regarded as scientific mission rather than technology demonstration mission. So it is science mission aiming for carbonaceous asteroid sample return and internal structure study of such asteroid. These two asteroids are targets of Hayabusa and Hayabusa 2. On your right hand side, the asteroid called Itokawa, which is a stony type asteroid. It's half kilometers across. It was visited by Hayabusa spacecraft. On your left hand side, it looks like a top-shaped asteroid. It's called Ryugu, which is a carbonaceous type asteroid, and it was visited by Hayabusa 2. These two asteroids has a similar orbit around the Sun. The perihelion is just inside of Earth orbit, and aphelion is just outside of the orbit of the Mars. Once the spacecraft arrives at asteroids, there's a way to study the surface and interior of such bodies. That technique is suited by the depths and the resolutions of the sensors. So for the largest and for the global differentiations, we can look for a large crater and family of disintegrated asteroids. And the radar sounder and tomography and seismic network and the microgravity measurement and the landing radar can tell us about partial mass or global fractures and robopile structures. Once we bring the samples back to the Earth, we can study the in microtomography technique for the gardening and the UV irradiation, dehydrated minerals, and all other uh, astromaterial informations. However, the intermediate scale, like a mesoscale, between microscopic sample analysis and remote sensing data from the mothership, it is achieved by the surface element, such as rovers, hoppers, landers. So the border and group and sample return from by artificial cratering and surface uh, sampling. So those are the ones that we should focus on, the surface sensing technology. Hayabusa 2 has carried one micro rover called Mascot, provided by German and French collaborators. It's a dedicated landing package for in situ science on small body surfaces, and it's completely autonomous on asteroid operation and with uprighting and relocation capabilities. Total mass of this robot is 10 kilograms, and they carries a number of scientific instruments such as magnetometers, a radiometer, a wide-angle camera, and micro-omega, which is a multispectral imager. So the Mascot was delivered from the mothership Hayabusa 2, and then it's landed so-called Alice in the Wonderland region um, after a couple of hopping of the borders and the bouncing and the relocations. And it has had 3 asteroids day or 16.7 Earth hours for scientific observations for both daytime and nighttime. So this is a close-up image for both Hayabusa taking Itokawa's image and Hayabusa 2 taking Ryugu image, and especially from the Mascot. For the Ryugu, there's a morphological resolution is much higher than the case of the Itokawa. Mascot also carried LED lights so that it enables to observe the surface texture of borders even during the night. Indeed, during the night color image, there are quite a few white spherules or spherical features are found. These are quite resemble to carbonaceous chondrite chondrules, as well as dark matrix and CAIs. So this is actually the very first direct evidence that indeed carbonaceous asteroids may be a home of carbonaceous chondrites. And also, Mascot revealed the physical property of the Ryugu surface by measuring thermal inertia and microporosity with suites of those instruments. So these are almost impossible for mothership, which are only hovering several kilometers above the asteroids, and it is only possible by surface rovers. In fact, Mascot is not the only rover which arrived on the surface of Ryugu. Japanese Minerva series rovers are also on the surface of Ryugu. Minerva was originally developed for Hayabusa 1 mission, That time there's only one rover, but it was not able to reach to the surface because of partial malfunction of the mothership. For the Hayabusa 2, we carried 3 Minerva rovers, and 2 of which have a capability of mutual networking. So it's called Minerva 2-1 series. Those 2 identical rovers are actually the first multi-station network on the celestial bodies. So that 2 rovers are functional and then both taking images on the surface, and then they communicate each other to potentially exchange the scientific information, and then eventually transmit to the mothership. So the right hand side is the one of the rover's picture of the surface of Ryugu with the sun appear to revolves. Okay, and then once the mothership comes to briefly touching the surface, that's also the opportunity for us to study the surface property of asteroids. So that Hayabusa 2 has the capability to have multiple surface touchdown or touch and go sequences, which lasts about 1 second. And then we have so-called target marker, which is artificial lighthouse deployed on the surface, and then the mothership will actually tracking such a artificial landmark, which is over here, to see to follow by the optical navigation. Because of the telecommunication is almost 17 light minutes away from the Earth, so the last touchdown has to be conducted by spacecraft fully autonomously. And touch the surface, and then after 1 second it just hovers again to ascend. So then you can see lots of pebble ejector floating around. So the first touchdown was a surface sampling. Now we want to challenge subsurface sampling, which would be the first. In order to do so, we have to deploy so-called artificial cratering experiment by a so-called small carry-on impactor, SCI in short. And the SCI technology is a hybrid approach between ground technology spinning and spaceflight heritage of deployable selfie camera developed by the Icarus or solar cell mission. And once the impactor created the artificial crater, it's about 17-meter diameter across. Ejector curtain development and attachment suggest that there was a gravity regime of cratering occurred by 2 kilograms of copper projectile at 2 kilometers per second of the impact speed. And then we are attempting to bring the spacecraft very close to SCI crater. This is once again its target marker, it's artificial lighthouse, and that's where the second touchdown was achieved. So the second touchdown looks similar on right top from as the first touchdown, but this time we just fire the metallic projectile and fracture the surface, and then we get samples. In fact, we are expecting in the microgravity condition a few grams of sample collection per shot. according to microgravity experiments on the ground. So then both Hayabusa 1 and 2 delivered the Earth return capsule to South Australian desert called Umila in 2010 and 2020 respectively. For the Hayabusa 2, we have already confirmed that there's a 5.4 gram of solid samples as well as both gas samples are collected and then now returned to Japan for the initial sample analysis, which is in progress. Okay, in conclusion, JAXA has proven that deep space mission can be significantly enhanced by microprobes and rovers, especially for the surface elements. NASA's OSIRIS-REx explored another asteroid called the Bennu and for the sample return for once from surface, but there's no surface elements associated. Incidentally, Hayabusa 2 has now left Earth again for its extended mission to another asteroid called 1999 KY28. I stop here and thank you very much.
Thank you, Hajime. That was wonderful. Did that come across okay with you guys? I couldn't tell so much from here. There are a few places where I had to start it, but good to hear. We can open up the floor to questions. We have a few questions. I don't know if Kalind is here from JPL yet, but oh yes. Hey, Kalind, good to see you. So we're going to take a few questions from Yano-san, and then we'll transition to you if you don't mind. So any questions? Just go ahead and jump in. I guess I could ask one. How do the micro rovers actually navigate? You know, I know that some of them have asymmetrical crew masses and they hop, but can you actually govern where they go to some extent?
Yes, thank you, Joe. For the mascot, it has only very crude directions. It has control of the straight axial torque. Depending upon which torque you rotate, that you by the counterforce you can actually the hops. So it's a kind of crude directionalities, but how far it goes, how long it's keep bouncing and stops, there's no control for it. For the Minerva, it's a quite similar concept. However, Minerva has more delicate control of torque, so that it can have a small hops or large hops. And in fact, the Minerva 2.1 actually traversed almost 70% of the area of Ryugu. So it comes back and forth, but completely autonomous by having angles with respect to the sun and also local slopes.
That's great. Questions from anybody here? You can just speak up if you like.
Sorry.
Go for it.
Oh, thank you. Sorry, Professor Yan, impressive presentation. A quick question: how did you decide where on the Yugu to sample to take the sample and where to deploy the mascot? And how did you decide which position is more representative? Thank you.
Okay, thank you very much. It's an excellent question. In fact, the number of criteria when you look for so-called landing site selection. But for both operational reasons and scientific reasons. For the scientific reason, as you pointed out, we hope to collect as representative location as it can, for which they represent entire asteroids. But for the operational reason, we have to have spacecraft safety. Otherwise, we can't bring the samples back. So the priority wise, operational safety comes first, and within the possible landing location candidates, which have a goal for the operational restrictions, then we can start to narrow down the scientific reasons. But however, the Yugu was so border rich, and then there's unlike the Itokawa's smooth terrain, so that we think there are quite a few areas localized in terms of homogeneity. So then we try to find the equatorial region, which is geopotentially low region, so that's the most of the samples collected from different locations. And then for the second touchdown, as I or my video showed, it has to be very close to the crater we artificially created, so that we have a high hope to bring subsurface samples. So for the second touchdown, it's we really have to come to the cratering locations.
Thank you.
Okay.
Great. Juliana, you had a question regarding the sample pickup.
Yeah, if anyone else wants to go, though, they should take priority over me. Well, okay. So Hajime, my question for you was to speak a little more about your personal experience collecting samples in the desert, especially during a global pandemic, both in terms of localizing the sample, like the technological challenges, but also the societal challenges right now. Maybe you have some pictures even to show.
Okay, yeah, thank you, Juliana. Yes, the major difference between sample pickup in 2010 and 2020 is that 2020 we have to face the pandemics, and it is the Australian Space Agency and South Australian government are so helpful for us to define as essential workers for firsthand. But still, we have to follow all those self quarantine period. So that before departing from Japan, we had 1 week of voluntary quarantine period, and then once arrived to the Australia, we have straight 2 weeks another quarantine, and then we have a dedicated bus all the way straight to the Umel Desert. Umel Desert is a military asset, so we always have to be escorted by the local officers, although we have to drive ourselves. So once we arrive to the desert after those 3 consecutive self-quarantine period, I think we are one of the cleanest troops and the safest troops in entire Australia. So that way that we are quite confident that we could do it in a healthy state. But that's the sociological aspect. And then for technical aspect, how we can allocate the capsule landing site. Before capsule lands, we have it's a nightly entry, so that we should be able to actually triangulate the trajectory of the capsule as a streak of light, just like artificial meteor. And plus, once the parachute deploys and decelerates in dense air pressure, then there's the beacon antenna start to transmit the radio signals. That's once again, it'll be triangulated by the ground antenna system. And then lastly, we also have ultrasound and also the shockwave detections. So those 3 independent detection system can really narrows down trajectory. And then for the last portion is that we deployed helicopters for the visual confirmation. We had carried a drone for the backup, but we didn't need it because it was quite obvious that the visual, the search from the helicopter was good enough.
It's great. It's one payload you don't want to lose. That's for sure. Go ahead.
Well, I was curious about the end of the story too. Once you actually locate, how do you then reach?
Oh yeah, I mean, one of the things that we have to do is that we have to ask indigenous people that if we could land them, because most of the time those areas, the mythologically holy places for them, so that we make sure that where we land and where we fetch our capsule is permitted by local people. And once we get such permission, we just go for both helicopters and then later by the four-wheel drive.
One more quick question, then we'll turn it over to Kalind and let you get some sleep. One of your rovers was battery powered, I believe. The other two had solar cells to recharge what it looked like. Of course, in Giotto, that was a problem because you got into a bad place and it couldn't recharge.
Right.
Did these things last? Did you have features that put you in too much shadow, or how did they hold up?
Okay, yeah, of course, it's always the danger that like Philae lander for the Rosetta, it was just
sorry, wrong payload here.
In very, very deep deep valley, local valley of the comet Churyumov-Gerasimenko. But for the case of Ryugu, of course we were anticipating such risk. That's one of the reasons why we had a two. But we ended up it's quite good, long-lived. It's at least one rover lived more than 50 Earth days. One of the reasons for that is that rover, which is completely autonomous, was actually followed where the sun is. And also of course, but the asteroids rotates 7.6 Earth hours. So that means a rover inevitably stays in the night as well. So that once it's coming to the night or the evening, then it starts to sleep. So that the rover only moves during the early morning of the asteroid day and late afternoon of asteroid day. So during the noon time and the night, it just sleeps there. So we call bedtime and siesta time.
Great, exciting to see how well it worked. So we should let you go. Thank you so much for staying up and sending that video.
Thank you very much.
Great to see you again. Look forward to see you again soon, Hajime. Bye-bye.
Bye.
So we're going to shift gears now to our second speaker, Kalind Carpenter, is with us from JPL. Some of us have been fortunate to visit JPL the last years. And on my last visit, I was totally blown away by Kalind's talk. He described the EELS project, which is, you hear about it, very daring mission to really explore the oceans and the vents of the icy moons. And, we all look for things to live for. You want to live to see your grandchildren and stuff. Yeah, that kind of counts. For me, this counts. I want to live long enough to see this mission and find out what's under the ice there. So, Kalind, take it away.
Excellent. Well, first, I want to thank Hajime. That mission was one of the things that made me feel connected to our industry, to space exploration, again, from work for home. I'm in the cabin up in Mammoth now. I don't get to go in very often. I got to go in for the landing, which is great. Pretty soon we get to put this robot together. But watching robots descend down to the asteroid, bounce around, get their samples, watching all of that has been one of the most inspirational things I've got to see recently. And then seeing them collect the sample and getting a nice size sample back from another body was something that just had me riveted. Now there's many successes since then, but this is something that has meant a lot. So thank you very much. Yeah, we have a lot of good things going on in space. It's the place to be right now. I'm going to tell you, as I told some representatives this last week, about what we see as the next frontier. It's interesting that the future of space exploration appears to be underground. And similar to this idea of needing to get that subsurface sample, because that's the pristine sample, that's your pay dirt, that's the high science return. That's very much what we're looking to do. So let me share this presentation and you'll see what we've been working on. I have a very good internet connection, but please let me know if you have any issues hearing me or anything else. Sorry, my face is all washed out, but I'm right by a big window. All right, so this is the Exobiology Extant Life Surveyor. So this was a robot that was conceived of once the ladder of life and the kind of a definition of life that's fairly agreed upon. It's something we're still working on, came out. But once we knew what it was we were looking for, we start figuring out how to look for it. And we have instruments now which have the sensitivities and the levels of detection to start looking for life, right? In general, though, no one's going to fully believe it, just like we have an asteroid here from Mars, which some scientists say there's evidence of microbial activity on. And some of the scientists for Viking back in the 70s believed that they had found life because they saw some chemicals they put out overnight consumed as if something ate it. But there's debate whether that was perchlorates. So what is Carl Sagan's quote? Extraordinary claims require extraordinary evidence. So this is conceived of to get that evidence, to actually see extant life, not frozen, not something that like Perseverance right now is looking for essentially fossils, right? Will we be able to determine whether that's a fossil? Will we not? Depends on the size of this. Is it single cell organisms? But if we start seeing something swimming or breathing, and we do have the ability to tell if it's Brownian motion or not, if we can actually see a metabolism, metabolites, things being converted in a way that we then do have to prove that this isn't some form of advanced abiotic chemistry that we don't have on this planet. Remember, there's life everywhere. We just went through what, 3 kilometers of ice and ran into a rock and found sea sponges and other life forms underneath. Life is pervasive. We don't even know how deep it gets into the crust. We know that it doesn't need sunlight. So life on this planet is everywhere. We don't know if that's the case elsewhere. And one of the interesting questions may be to find it, but it may be to find a pristine environment without it, so we can understand what leads to genesis. So here's some of the controlled experiments we're looking at doing towards these questions. So Saturn, we thought, was way too far away from the sun for there to be active moons, any liquid water, or potentially life, because at the time we thought you need photosynthesis for life. We thought you actually needed contact with sunlight, right? So it's amazing how much just our viewpoint on this has changed. So Enceladus is tiny. It is the diameter of Texas. It's actually an 87th Earth gravity, but we'll just say it's 100th Earth gravity. It's very young at the South Pole, so it's about 1 million years old. The ice shell thickness is only about 1 to 5 kilometers thick. Right, this isn't any of those 20 to 40 kilometer thick ice sheets that you're going to find on a lot of the other icy ocean worlds, right? I mean, we live on an ocean world. You don't need an ice shell to have an ocean world. And then plume, it's confirmed that there's definitely a plume, even though I would say we've confirmed there are plumes on Europa as well. Another really nice thing about Saturn is it has less radiation than the Van Allen belt, right? So you get right outside of our atmosphere, there's actually more radiation around Earth than there is on Enceladus. So it's a very benign environment. So here's some images that we have of it. So this is a Cassini image where we first realized there was activity, but a lot of people think these are short-lived phenomena. So we went back and looked at some of the Voyager data, where unfortunately there wasn't, the gimbal didn't work at the right point to be able to look at the moon in more depth. But upon looking at the information again, you actually see that the South Pole did have, these geysers essentially coming out of the South Pole 40 years ago. So in the modeling we've been able to do, we know there's active jets. So the South Pole looks like there was activity at some point in the North Pole, but that's heavily debated. There's also another interesting location, but we know there's probably a rocky silicate core because Cassini found silica. In fact, some of that's coming up. We also have thermal information from the South Pole, from these tiger stripes, these 4 parallel rents in the surface. And looking at this thermal imaging, we can see Damascus Sulcus, which is that one on the left, either has the thinnest ice or it has the most mass with the thermal inertia, because it comes out, somewhere around 0C above it. If it has the most mass exiting, the most mass flux, we know it has the largest conduit, which is easiest for us to get through. The assumption here, which is one that's, fairly well substantiated, is the ocean's a constant pressure, and then all of these are basically fed by a bulge chamber underneath. So there's going to be a normalization of your initial conditions. If the initial conditions are the same across the 4, then the one that has the highest thermal flux is either going to be thinnest ice or the most mass flux coming out of it, which would mean the area that's coming out of is the largest. So that's the one we're looking at targeting. So some of the things that make this super interesting is we found there's water, carbon dioxide, methane, ammonia, molecular hydrogen. The existence of the hydrogen is very fascinating. There has to be enough energetics to be splitting the water oxygen, the water hydrogen oxygen bonds. And so this is probably serpentization, and finding the silica that we found here as well. This is just the this is the salts. This tells us that there is very, very likely magma water interaction. So if there's magma water interaction, we start getting hydrothermal vents, right? It's a foregone conclusion. You're going to have heated water that's touching magma. You're going to have a lot of minerals that are going into solution. As soon as it cools off, when it comes into contact with the water away from the rock-water interface, that's going to precipitate out and build hydrothermal vents. So hydrothermal vents have a different pH on the inside and the outside, so they're fuel cells. So you have this constant charge going across the walls of these fuel cells always. So you now have chemicals that we know we need for life here. We have a habitable ocean, and we have energetics, which are always going on. And it is the leading hypotheses for where the genesis of life happened on Earth. But once again, like I said, because life ate all the complex chemicals that could have led to that, we don't know we'll ever be able to figure that out on Earth. So we have to actually go somewhere else to see if that hypothesis is correct, or we need to build up to it in the lab, which some of my friends are doing. So there's a couple options. But a really nice thing about the Cassini data is, right, this is from 2017. This isn't as old as Galileo data. We have our digital elevation maps, and you can see this one on the left. It might be 1 million years old, but we have about 1 millimeter a year deposition rate of the plume ejecta falling back down. So like the snow outside my window, it's going to fill in all your cracks. So I believe each of these is about a 1 meter per pixel resolution. So our spacecraft could land in a pixel anywhere in here. But because of that added process, we know that we're likely to find many targets to be able to land on. And then we have this nice downhill going into the middle of the crevasses where we want to get to. All right, so here's the hydrothermal vents I was talking about. There's going to be a really good planetarium show coming out talking about more of the science behind this. So I will let you see that. Now, I'm an engineer, Engineers have to go off of this data, and they have to take the assumptions and the models being made by the science community and translate it into a technical capability. So we're looking at the skeet shoot images. So this is the same images processed two different ways on the right and the left. On the left, everything looks really rocky, correct? On the right, it looks very covered in snow. You can also see on the right, it looks like there's circularization. And this is the Kalind-Porco idea, where there's about 101 different vents, and each of these is going slightly different directions. And then you have your kite and Rubin model on the left, which is your open crevasse. Well, it turns out the way that these are being mapped and created, the one on the left artificially increases the elevation difference between the information. The one on the right is from Paul Schenk. It's a little bit more of a black box. We don't exactly know what he's doing. I'd love to sit down with him when all this is over and figure it out. But he has some great papers on the snow-like, kind of characteristics we're likely to find around here. So my guess is it's somewhere between these. But what do I have to do? I have to design for both of them. I have to take the worst case. In fact, I'm going to take a worst case between both of these and actually increase my envelope. So here's the two different models. Now there's more going on than that. If it is the Kite and Rubin model on the left, this means we have an opening and closing of these crevasses, and basically from the vapor pressure of water coming into contact with the vacuum, you're going to have boiling ocean. This slow boiling through this large area is going to give you very low forces. In fact, you could probably fall down the one on the left, depending on the width. If it's any bigger than about 0.8, actually, that's not even true. That's taking a circular cross section. The one on the left is the trivial problem as far as accessing the ocean is concerned. But the interesting thing about it, it's also the one that means a fly through and a landed mission is likely not going to be successful, because you're going to, instead of having these jet drops, which carry a lot of pristine information, being driven like a soda bottle that's been shooken up. The one on the right is your cryovolcanism. And the way this works is before you boil your water, you have your dissolved gases, where we know there's the CO2 and hydrogen and other things in the water. As your pressure goes down, they're going to essentially start expanding, and they actually drive the liquid water while it's still liquid out by the expansion of the gases. So your forces are a lot higher for the Kalind-Porco one, the one on the right. The one on the left, what happens with this slow boiling is you have the gas go up, and the question is there enough water vapor that it refreezes, and are the other volatiles and potentially any solids able to refreeze onto this crystallized center? And there's a lot of modeling saying likely, but what are your limits of detection, and how diffuse and distributed is this if you're trying to fly through it? And also, how much sample do you need to get from the surface, and what is the reprocessing that happens both through the boiling and when it lands back on the surface? The one on the right, however, is going to be blasting likely liquid water. Your triple point may actually be above the surface for the one on the right. All right, there's some interesting heating effects and like friction type effects that will keep things from freezing right away. It's also the harder case to get to the ocean, but there's a better chance you'll get your pristine samples on the surface. So because we have this duality, we have the ability to design a mission that we feel will be able to conclusively get a pristine sample from this ocean and let you know what's going on. So here's some of the information. I started reading every single paper I could on Enceladus, and instead of arguing any of them, I just took them at face value and made a bound, right? There's error bars on these. Now there's a couple that were easily kind of thrown out. And so this plume throat, see that 2 millimeter to 150 millimeter, I left it there. But the low end is likely implausible due to the heat balance, right? So Cassini never saw these stop. And if you get down to 2 millimeters and you have a bulk ice temperature of 85 Kelvin on the surface, how do you expect at a 2 millimeter diameter your water vapor or water to stay a gas? And so we actually, I mean, if you've taken any heat transfer, you can do the calculation, be like, that's totally implausible. Don't know where that came from initially, but I leave them in there anyway. Particle size, we know a bunch of this from Cassini. So now that we have all of this information, we need to start looking at translating this into a robot that could actually accomplish all of these tasks. And so meet EELS. Afterwards, I'll ask you where you think the idea originated. And don't tell me this is the one that has a lot of what I already told you. Yeah, I'm skipping ahead. Ha ha ha. This is the one I was going to send to people that's standalone. There we go. Where are you at? There we go. All right. So yeah, Cassini, great things. And then we need to go back. Linda Spilker, who's the lead scientist, is actually helping us on this. She's a newly chosen JPL fellow, and she feels very strongly we don't need another precursor mission, that we have enough data to be able to land on the surface of Enceladus. And she's also the one who thinks very strongly that there isn't a secondary body of liquid that we need to go through.
Where there's water, there might be life. Let's take a journey.
That was not a great day for me. I found out my cousin basically died the night before. But anyway, so when we land on the surface, you can see how it flipped around to be the South Pole. Just to give the proper context. So we land somewhere near, we had this done in about a week. We're actually going to be putting those DEMs that I was showing you with the full topology in, so you can see it going down. I built a bunch of different sublimation and freeze anchors. That was an artist rendition of it. It works much more technically than that, but there are three, and you have your 3 points of contact. But once we put the face into the plume, we likely get that pristine sample. In fact, as soon as we got the contamination zone of the lander, we've basically finished our level 1 requirements of getting these samples and analyzing them. But regardless, we want to go further. So the robot's length is designed to be greater than the circumference of 1 meter crevasse. We'll probably adjust that to 1.2 as per a new paper that just came out. But by pushing on the sidewalls, we can generate much greater forces than your 1/100th gravity or your plume forces would be exerting on the robot. So this is supersonic, but this is a very rarefied gas, right? It's likely no more than 70 miles an hour winds would be here, which is sizable. Don't get me wrong, that is a lot, but ice, especially cryo ice, can very much overcome that. Each of our actuators right now puts out over 300 Newton meters of torque. If we do have that evolved case, the cryovolcanic case, we actually can convert into a self-driven screw. Now we don't have the mechanical disadvantage and we have less of a projected area, so we can push through either this throat or this crevasse where the forces are highest. Now, because of the weight of the ice, the water will be within a kilometer of the surface, right? And it may go within meters, tens of meters because of tidal flexing. So we don't need to get that far to likely be in the water. And once we're in the water, it's a swimming problem. In fact, on the surface, it's probably a swimming problem because it looks like there's not enough heat for the there's not enough heat for there to be sintering on the surface. So if at 100th gravity, you have a bunch of essentially snow that's non-cohesive and you disrupt it, it'll take no shear forces, it's fluidized, and we're swimming. So we're likely swimming on the surface as well. So this was a study we put together for both a melt probe and then 3 EELS if money was not a object. But the great thing about this is we got some really good artist work out of it, where the scientists spent a lot of time. You can even see we're going into the point where the South Pole will be facing away from the sun. So it's dark. It also means it'll be facing away from Earth, no direct to Earth transmission. So we have this orbiter that will be relaying the signal. The question is if NASA could get together, we could actually land before this happens, or we'd have to wait another 12 years for the sun to come up, or we'd have an orbiter. I'll leave that to someone way beyond me. But we went through the concept of operations. One thing I didn't talk about is because we're tethered, we can rappel down, right? It didn't make, well, I think we just didn't have enough time or money. This was done during our accelerator phase. So we essentially had 4 months where we put the concept together, and we just got through the concept phase that was 9 months, and we just got into a 3-year project. So let me take you into where we're kind of at. So we have this Enceladus case that everyone agrees is very important and is something we should be working towards. But how do you make this past the giggle factor? How do you make this something that people are like, that's not just a joke. That's not just science fiction. Well, we looked at on Earth, right? So our gravity equivalent of our 80 kilogram robot is actually very close to that 60 kilograms, force equivalent that we would have to deal with to go down against the plume. So we actually go up crevasses on Earth. And because it's supersonic, you actually have a similar force profile, right? I mean, there is going to be a bunch of turbulence and dynamics, but in general, you have a pressure difference. That pressure, because of the bow shock, will be acting across the full surface of the robot. So it'll actually be fairly similar to gravity. So we started putting together this robot that has the exteroceptive, or the remote sensing, on the nose, but we have a bunch of video. Actually, the video is probably in here, so I'll go through this quickly. We have a bunch of science, including the digital holographic microscope, science instruments in the nose cone. We can also put them later on. We have this active skin propulsion, this counter-rotating screw that works for fluidized media, but we're also using it as grippers. So having something that is gripping, and this is a gripping problem, we're actually treating this as a gripper. So by pushing outward, we actually look at the reaction force going inward, and there's some more of that coming up. So tether gives us both power and communication, and we're piggybacking off some work being done at JPL right now. This is the digital holographic microscope. This was done early. This is a smaller diameter robot, but you can see it fits nicely in the payload bay between the two counter-rotating screw actuators. So this is what I was talking about with the gripping problem. So we're actually looking at the reaction forces. And so what we did here is the trying to remember, I think the red is our predicted force and the green is the measured force. So what we're doing is we're looking to see how close our predicted behaviors are, also what our sensing is. So as you're going down through a vent, you're going to have, your multi-phase. You might have things icing over, you might have things fogging up. So can we rely on remote sensing? We hope so. We hope we can deal with that. And we've got a vacuum chamber where we're doing a bunch of tests. But in general, we need to do this all by feel. So that gripping problem I was talking about, the grip is actually internal, and instead of having cones, we're finding that we're having these interesting triangles, and as long as they come to a central point with 3 countering forces, we're able to maintain that grip. The other interesting thing is it works better as a surface mobility solution than I actually thought going into it. This was always conceived a little bit of propellers that was able to keep the center of gravity down the center, so you didn't have any pitchback moment, which at low gravity can cause a very unstable craft. But you can see here on Earth, on flat ground, we don't have any yawing. I actually did expect to see yawing. We played around with it to make it so we didn't get the yawing, and I was blown away at how well this is able to just go in a straight line. I'd always conceived of it more like this, where if you give a little bit of a bend to it, it would be able to maintain that, and we could just do this serpentine motion back and forth around rocks and whatever we run into. Let me see. Yeah. Let's move on to the next one. So another cool thing that we're doing in this, doing everything by feel, is we need to be able to conform to our surroundings. So you can see this robot as it starts coming in the corner, it just moves itself, conforming to the surface so that it can continue to exert even pressure, even force across its whole surface. So this is pretty awesome. with this robot, we actually didn't think it would be able to do vertical mobility, but this is actually vertical mobility with a bump in it. And you can see it is proprioceptively just conforming and continuing its move upwards. This robot, unfortunately, didn't have enough actuator torque. It's more on the like 8 Newton meters of torque compared to our 300 Newton meters of torque. That was one of the issues with stay-at-home order. We have not yet put all of our parts together. So actually, I've got a meeting on Wednesday about doing that. But some of the interesting things this robot uses to be able to get that torque in its small diameter is outrunner motors. And these outrunner motors are coupled to a couple things. This is a counter-rotating gearbox. And the crazy thing about this counter-rotating gearbox is its efficiency is like 95%. And I didn't believe it when I first saw it, but I ran the calculations myself. And it's because instead of reacting torque into stationary wall or stationary tooth, it's being used into a counter-rotating tooth. And so that actually increases our efficiency. I don't know if we're going to continue using this counter rotation. It limits some of our operational modes, but it is a pretty amazing engineering feat, and putting it together was a whole lot of fun. Now, the kinematics isn't fully locked in, but the reason why we have this kinematics is if you make a loop with your fingers and then you move it out, the projected area or the projected diameter of the robot changes while it continues to describe a circle, ensuring that our threads are always in contact with the outside. The other cool thing about this is you move the other direction and you get a natural camming action into the sidewalls. And the cool thing about using your rotational motors instead of what we call our shape actuators, kind of our elbows, is your mechanical disadvantage is only the diameter of the robot, so about 5 centimeters, instead of the full length to your next contact point. So we've designed this robot to only have 3 points of contact, but by able to have this localized camming action into the sidewalls, we think we can actually ensure that we have a lot more contact, no matter what the surfaces we run into are. And we're very much looking forward to finding out. The integrated sensing we need to do in this crazily densely packaged thing is amazing. So right now we're looking at a couple different ways of doing it, but one is actually using our strain wave gears as our torque sensors. So directly at where our greatest torque output is generated is also where we'll be measuring it. So that would be a very elegant integrated solution. We've been able to demonstrate some of that. Academia has demonstrated some of that, but we'll see if it is robust enough for a path forward. All right, so you know, Perseverance, when we started doing this, it wasn't called Perseverance yet, has to go 15 kilometers in 1.25 Mars years, which is 2.5 Earth years, and have 20 drilled samples. EELS needs to cover in 16 hours, so one tidal period, we need to go up to 3 kilometers. Now, it's not likely 3 kilometers, but there's some people who think the vents open and close completely within this. This doesn't match Cassini observations at all, but we can do it. So to deal with those models and naysayers, we can definitely get through. Because Cassini never saw them fully close, and because we have somewhere between a 300 and 600 micron tether, we're not worried about the tether actually being destroyed, especially the Kevlar cover on it is going to make it very robust. So this is what I was talking about, not being able to necessarily rely on the exteroception, your remote sensing. So this is someone actually putting a camera down Old Faithful, right? So you can't see very far ahead of you. It's never going to be a clear day with good visibility. And you have your liquid coming past you. You can see the gases, the different things. And we actually expect that things could be much worse if we have frozen particles, which are going to start bouncing light around. And also the sidewalls. Enceladus is the brightest body in the solar system, has the highest albedo. Everything bounces off of it. And this is likely created by the plume ejecta when it lands back on the surface. So we need to make sure we're very robust to that. So we actually have some things where instead of being deliberative, sit there, plan, wait for people in the loop, we have to be very reactive. Part of this is it's about 3 hours round trip time of flight to communicate with the robot. Because it's such a dynamic environment, we can't wait. The robot just needs to power through, even if it loses actuators or things go wrong. So we have a lot of fun things to test on Earth. Normally we make our robots very robust. 6 wheels is very overconstrained, even though I really love the rocker bogie suspension. We need to be adaptive, right? We don't have this ability to go over, a meter rock. We need to make sure that we can go around it, deal with whatever we encounter. A lot of our spacecraft especially, but our robots are protective traditionally. They have a fault, they go into fault protection mode, wait for someone to help them get out of it. We need to be resilient. We have a fault, many faults, we just need to go. So it's different than much of what we've done before. This flow guided navigation, a great thing about being able to follow these streamlines is this is why, in a sense, we will always have some remote knowledge, right? Someone pointed out that with supersonic flow, you lose any ability to propagate your information back down. But the thing that will always come forward is essentially what existed at the throat, at the stagnation point where you're at Mach 1. So at that point, if you run into anything else as well, that's going to be captured and that's not going to be lost. So if we get to a point where we're not measuring the stream, we know something's downstream disrupting it, right? It's not like water that will flow around a rock and then keep flowing. There's going to be a discrepancy. There's going to be a hole. And so we'll be able to measure that to be able to follow down through whatever might be in our way and avoid it without needing any forewarning by any vision system, LiDAR, or structured light. So this is some examples done by CMU of some bio-inspired solutions where you give these things a vector and then they just start moving and they know the shape that they're in, and when they contact something they have memory of that, so as they go through the sinusoidal behavior they can for the most part correct for and keep that trajectory going. And this is all done just by feel. So they're one of our partners on this, at least hopefully I have a conversation with them. It's very interesting where someone says yes, you guys get to move to the next stage, but they actually haven't confirmed our plan. So I'm very hesitant to say anything until they confirm that the full amount of money we asked for is on the table. But you can see there's some great work that's done here on Earth, and we can demonstrate more of this until everything's just extremely robust. We have no intention of going into space until all of this is done on Earth. The other thing is, with the exteroceptive, we think that we can actually do a bunch of post-processing. So we're setting up with this plume. We're actually doing it. I got on lab last week, hopefully quite a bit soon. I have these converging, diverging, tiny little nozzles coming, but we're basically recreating this. We have a high-speed camera and other cameras where we're going to look at the different properties we might be running into and what we can do depending on which type of camera we use or remote sensing we use to process the data so we can get our remote maps. And the reason why we want to do this is, remember, we're roboticists. We want to be able to plan. We want to be able to choose the optimum route through things. We don't just want to be reactive. But the nice thing is you can be. So we took our this is actually on the back end, the same system we do our rover planning. We just want to show people what operations would look like. So you can see the sensors sensing that should be mapped to this. Every once in a while, the robot stops, does this little shimmy. The shimmy with the nose is to actually determine where the pressure is highest and what the pressure is. We want to stay out of the middle where it's potentially higher because you won't have any wall effects. And so we want to, but it's not really true in supersonic, but it's very interesting. We're very excited to see what we'll run into. But you can see we have these different poses, and pretty soon I'll get a little bit more into the poses and some of the controls and how it's moving into autonomy. But this was done because a lot of what we do is operations. So when I was mentioning that pitchback moment, so this is what happens if you have your mass higher. And so this is why we went into the inline Archimedes screws instead of something that looks more like the tanks and different things you'll see in Siberia or here on Earth. So this is some good work that ASU actually has been doing, Dr. Hamid Marvi. So this is the difference when you drop everything in line. This was an early one. So in line, you no longer see that pitchback moment, that flipping action. And I don't know if I have it in here, but we wanted to see what happened when you, so this is the one that artists were modeling afterwards, but we do have somewhere some simulations of the robot burrowing. So you can see this was an early day thing. I did this in about a week just with some Amazon and Proto Labs parts. We did a bunch of it actually in a vacuum chamber. So just showed we could do the self-riding, the gripping, reacting forces. On the right, this is actually a vacuum chamber, but look at how fast you see that sheath growing around the temperature probe. This is why that evolved case is something we're heavily designing for. Now, this isn't supersonic, but this is, melted water vapor. And you actually see we get liquid water in there when it drops, because you only need, was it 0.006 atmosphere to have liquid water? So triple point of water is actually really low. So we can generate these forces internally. That's something that I have some of the science team looking at, is where might we run into the triple point of water when we're going down the vent, because we want to be able to make sure we can do the right science in those locations. But yeah, we've got some tests to see if at supersonic speed you still see this, or if this formation is completely disrupted. But I love just watching these phenomena and figuring out how it works. So we're building an Earth-only robot to do Earth science, to do search and rescue, potentially DoD applications, really prove out autonomy, with the goal of creating an Enceladus capability to get to an alien ocean within our lifetime. Thank you.
Thank you, Kalind. That was fabulous. Wonderful to see this mission develop. When I was there, you actually were pretty aggressive about a timeline, grabbing an SLS manifest and looking at like 10, 15 years. Is
Yes.
that's still what you're talking about?
I want to be on the radar before the decadal survey comes out, and COVID's really put a wrench in things, but then being chosen by ourselves as the only project moving forward in the program that we're in right now, hopefully will accelerate it. So my conversation tomorrow will essentially be, is part of the scope of this project helping to get a 2031 launch. That's my goal.
That's great.
And that's the NASA kind of earliest we could possibly make it happen. So I did present it to a senator and some Congress people right before, half an hour before the landing last week. And they loved it, talked about having us come out. The science is coming together. The team's super excited about a bunch of the Earth applications. If we can get the funding to do the parallel development, I do think that this will be past the giggle test definitely within 2 years. My hope is within 1 year. We have a chance in July, if the robot's together in a good state, of having it go explore some caves in England while it's controlled from Pasadena, showing some of the ability. And then if we get the funding and the go ahead, we would love to have a non-tethered version help our subterranean challenge team, our DARPA challenge team. I don't think we'd be much help, but the thing that we can do is where you have rubble piles, we can go over the rubble piles without, the risk of falling, like they're like the walking spot mini, or kicking up a bunch of dust like any of the UAVs, right? So it does have a mobility that isn't captured within our current fleet. So those are our near-term kind of goals, but we do have 2 trips a year to Svalbard planned. So we would like by year 2 to actually be demonstrating a lot of this in crevasses and moulins in Svalbard. And by the end of year 2, our goal is actually to have accomplished it, which looks like it might include science site selection and science sampling and handling and in situ readings now. So we need to make sure they increase the budget accordingly and get that team on. That's actually one of the meetings I just came from. But that's really exciting for us because we actually get science results here on Earth, right? And I could be at many different places. Why do I work at NASA? Because I get to have lunch and coffee with scientists, both Earth scientists and other ones who give me fantastic insights into questions we don't know the answers to. And then we can set up experiments that need technology pushed to a place that we can feel we can conclusively get those answers. And that's when I start getting really happy, because if I did not work at NASA, that's what I'd be reading about. It's what I'd care about. It's right. What I wish people were producing more of. So
yep, we're right on board with you there. It's great to see you really being able to be so bold with the timeline, but actually look at it as being very feasible and having all these other applications that drive it too. You have to also have a lander design at the same time. And I guess for deployment, is this thing going to get coiled around the lander and then uncoil itself with the tether? Because you don't show that here.
So these ones actually come out of each of these legs.
Okay.
So they actually sit in here. And the cool thing about these, I've got another image somewhere. They have a UV and IR light surrounding it.
Mm-hmm.
So the idea is these would be, because it's basically the same unit n times, we would have them robotically assembled within a vapor hydrogen peroxide bath.
Mm-hmm.
So it's essentially a plasma, very oxidizing plasma that will even eat the skeletons of most of our Earth life. It also degrades all of our materials and our electronics, but
yep.
we can characterize how much it degrades them. But then on the outside, on the surface, there's chance for recontamination. So we actually have 10, 12 years of reduction of any type of bioburden, which they say will sterilize the whole thing. So one of the ideas, though, that I liked, they liked them just dropping out of these. So what's not shown here is it is a 1 meter long tether spool that goes on the back. And we actually have those so they pop off when you have removed all of the volume inside of them. And then that actually works as backup repeaters. That's actually something which I think I have the funding for. The thing is, that's a separate task. They have their own $5 million to produce these high voltage high efficiency tethers.
Mm-hmm.
And then I'm hoping to just do the spooling unspooling mechanism with this ability to drop off each of the units, so we have less mass as we continue down. Because remember, that's not driven. That's basically just going to be passive. So we have the ability to hold that off the wall, but as that shortens, it's going to be easier.
Yep.
So yeah, that's actually, funny enough, everyone agrees one of the most important things, and the thing I get the most questions about, but they felt it was so important and so expensive, but they knew we could do it, therefore they didn't want to fund it. So I'm hoping it comes back in.
Yeah. And so the power is coming down the tether. It's distributed, and these spools actually will have RTGs in them, or is
so right now planetary protection doesn't let you bring radioisotopes to the ocean. Okay. That's actually why tethered, but we do want distributed power in form of batteries. Yep. Especially if we have these repeaters. The thing is tether death is definitely the weak point in this whole concept, right? Because we've been able to, communicate with the Voyager missions for 40 years. Yep. So there's, with the low radiation environment and the thermal stability, there's no clear thing that would actually end this mission other than breakage of tether.
Yep.
So we want to then extend it by having batteries internal to have distributed power. A lot of that is, so it's really only a 50 to 200 watt robot, depending on how many instruments we're running or what's going on. But currently, at least for Earth calculations, we will be at like a kilowatt when we're going through that point where we have to use every single actuator and really produce all that force. So the way we want to do it is actually have localized batteries that work as power conditioner and also ability to do fast draw for huge power bursts to get through these points.
And once you're through the crevice, then that's it. You run on instruments, but you don't necessarily have to actuate so much.
Exactly.
But the data has to go back through the tether, so it still has to survive, at least until you get a radio link or something. You got to have a data line back.
So the cool thing about the data line is it's fiber optic right now, covered in copper. And that copper does two things. It makes it so that it's harder to bend. So you're less likely to get a bend radius that will start giving you micro fractures. The ohmic heating actually helps to heat the glass. So it's also not as brittle. And it's also why we need to be up at like a kilovolt from the lander. So like I said, that's a different effort, but that means our I squared R losses are going to be lower. And then the other cool thing about it is we've been looking at doing the 6-core fiber optic sensing system ones. So right, that's only added 100 microns. That's why I said it's like 300 to 600 microns, depending on if we do the sensing. But the reason to do the sensing, even though you have about 3% error, is that could be how we do our global localization. We just localize off the lander through the tether with our error bar. And we always know where we are in respect to the lander. And so one of our biggest worries is you try to go down the vent next to the vent you actually want to go down, and then you're not successful. That's why this one is 3, but there's a good chance they'll never pay for 3. So we need to make sure we go down that one with the biggest mass flux, right? And so it is very important that we're accurate.
Ideally, you take your time before you take the plunge and figure out where you're going. Anyway,
we have a lot of science goals on the surface, and like I said, all our level 1 goals are on the surface. And the cool thing is this is a mission that keeps giving. Well, it's 12 years to land. 4 of those years is taken pumping down around the other moons, including Titan and Saturn. So you're going to get lots of passes of all the other moons. And then to be in orbit around such a small body, you're not moving very fast unless you're very close to it. But then we'll be able to have ridiculous like pinpoint accuracy in landing because you can essentially hover. And the robot's super dense, but at the 100th gravity, we don't care about buoyancy because your water mass is the same. And we can, with very, very low power, essentially accelerate that mass and keep ourselves right at the ice water interface. So it's great that like Earth, we have to worry about buoyancy, but Enceladus, we don't. And we're trying to like, how do we gravity offload it on Earth? Do we gravity offload it? Do we just make a bigger one we can make buoyant? It's pretty fun. There's a lot of solutions, fortunately, but it's interesting.
And it'll be standard practice after you run this mission. So this is the flagship. If you have a chance, can we open up to a few questions? If you can hang around a little bit, we'll have to go to the class session in a few minutes. But anybody, I have a question for Kalind. Just jump in.
I had a question. Fantastic presentation, and I've actually followed the EELS project pretty closely. I know a few people at JPL that have told me about it. I had 2 really quick questions. You said that it would swim. There's like a swimming motion after it sort of penetrates through the ice. Does the EELS have that capability, or is it just going to kind of hover in the water?
We're kicking to academia because the question is, does it swim like an eel? I got an eel right here that actually, swims, or do we just have propellers, use the counter-rotating screws as propellers, or do we just actually put underwater, kind of like torpedo propellers on the back of it that we know we can have control authority of, and does it have some pop-out control surfaces? So there's been a bunch of architectures generated. This is another one where initially we weren't doing underwater mobility because they're like, well, we know you can do it. We haven't seen you do it, but we have confidence in it. But one of the co-inventors, Mike Yip at UCASD, he's right by Scripps, San Diego. They're building one anyway. So I'm very interested to see what he comes up with. But what we'd like to do, if we can, is build enough of these, we can get them out to universities to start answering some of those questions. Because one of the first things, CMU wanted to do is do like sidewinding. But the thing about the screws is the screws are sidewinding. right? That's the thing that came from Professor Marvey, is he did sidewinding snakes and realized that they leave behind your screw shape. And so he started doing the screw mobility because it works really well for unconsolidated media, right? Where I was looking for fluidized media, but they tend to be pretty close together. So there's a huge amount of bio-inspiration, but especially as we start making it so that actuators are no longer coupled, you can do things like I had one where only 4 are in contact and you're rolling. I had it so it can roll up and down, or it can start doing the spiraling action. But what happened is within JPL, they love just seeing a single thing, a single kind of gate, a single way of being operated, and that works for everything. So that's what was demonstrated in the animation. We know that a lot more could be done. And so what we want is to get these out to academia, private sector, whoever, to start developing what the real Earth capabilities are, furthering the autonomy, furthering the use cases, because like I said, what we're building is a state-of-the-art Earth robot, but we want it to be an Enceladus robot, but that development should be done community-based.
Well, I work with the Woods Hole Oceanography Institute, and I'm sure we'd love to have one. So,
all right, well, put me in touch with them for any use cases, because we're looking at accommodation. And as long as we get the accommodation in, it's something that we can either hand off prototypes we have, or potentially if people want to pay the delta, right? This is a cost. We can't make any money in like a next iteration. We can get people these. We've looked at smaller ones to drop down Mulans, because you have the freshwater plumes that go underneath the ice sheets. And my personal goal, if it was for Earth science, would be to drop these down Mulans and have them follow that they'd have to be neutrally buoyant in this case, but follow these freshwater plumes and map the freshwater ice interface while they're getting salinity and turbulence and mixing, because you have the warm ocean water coming up onto the continental shelves. And so this is what's leading to some of the catastrophic calving that scientists don't have any concept of, because they can't see under the ice sheet currently, and they don't have models of this interesting shape that you have, or the seasonal variations, and how to move that into their continental size ice sheet models to start predicting some of this. And from the standpoint I'm as, you can't send humans out to a lot of these locations, because the catastrophic kind of calving plate ice sheets are the ones that are the most dangerous. In fact, you can't even have a ship come close to the front of it. But if you could have a robot drop down, go underneath it, go where there's these calving icebergs just all around it, and give you data on that interaction, what's driving it, what kind of the magnitude of the different functions are, of the different variables, that would be huge. And it would be a place you don't put people, therefore robots. So I'll see if I can ever convince NASA to do Earth robots for Earth science, because they have this idea. They do instruments for Earth science, and scientists then use them. And they do robots for space through our Space Technology Mission Directorate. And it would take an act of Congress for those two to commingle their funding. Very unfortunate.
So some things are in a different class than the science challenges, I guess. Any other question for Kalind while he's here?
I got a quick question. So the icy moon, the EELS gonna explore seems extremely freezing and also wet. There's water vapor inside the plume. So as you mentioned, the EELS has a very sophisticated mechanical system, and in this harsh environment, the mechanical system might get frozen and stop working. How the EELS fight with this? Thank you.
That is a fantastic question. In fact, I was just talking to 2 thermal engineers earlier today. In a vacuum, we actually have trouble getting rid of our heat. And if we're actually running through a kilowatt of heat, that's a lot of heat. And so getting too hot is more of our worry than freezing up. So do we have issues with getting water inside? We definitely do. So getting the The thing is, those under 10 kilometers of ice, you're only talking about what, 10 meters Earth equivalent. It's 40 kilometers, I believe, more down to the rock water interface. So you're talking about 50 meters Earth equivalent. So that's just beyond where humans are allowed to, with a recreational diver's license, dive down to. So this isn't huge pressures that we're talking about. This is pressures we can deal with. Then the getting rid of the heat, like I said, is a huge issue. But the point at which we need to get rid of the heat, we have forced convection. And the other nice thing about that is the amount of heat we produce will be directly proportional to the amount of force we need to counter, which will deal with the mass flux that we run into. And the greater mass flux, the greater thermal ability for the plume to remove our thermal heat, right? Because we'll be getting either boiling off of the surface if it's low pressure, if we get any water vapor on it. So evaporative cooling is awesome. The forced convection is going to be quite good. So in general, we think that that will work out. But like I said, we need to make sure that the scientists and the thermal engineers have a design that closes.
And
Thank you.
in terms of the sensor payload, I mean, it's great to see that you're doing this holographic microscope. We've been playing with those too in our environmental sensing stuff, at least beginning to look at deploying some of those in the field. But there's also the idea of DNA probes. And if you're going to put something into that water, you probably want to sequence or at least get some idea of looking for the molecules of light directly. What kinds of things are you thinking about putting on it?
Well, so the things that we're looking at right now, so for Earth, we have 2 workshops coming up, and we're looking at the Enceladus instruments we want, then the Earth science we want to do, well, the Enceladus and the Earth science, and then look at where there's crossover. And then we want to look at the instruments, look where there's crossover. Then we want to design an experiment that gives us state-of-the-art Earth, science data product. But then we also, from that, will be able to show that that concept of operations will work on Enceladus. So that's still a little nebulous. The things we know we can fit, other than digital holographic microscope, is the CE, was that the capillary electrophoresis, and then the LIF, which is the, was it liquid induced fluorescence, and then what are some of the other ones? We definitely want to do your resistance. So one of the things that Lori Barge really likes is if you just put electrodes across something and run voltages, pulse voltages, different voltages over it, and you read the resistance, you can start understanding the chemical reactions being created by the electrodes. And so over time, you can get a really good sense of what's going on in those locations. And she said for some of the astrobiological goals, those work out really well. And those are tiny. So we could actually put those in the sidewalls of every single one of our modules, and they would double as contact sensors. So yeah, there's some things like that. For the DNA sequencer, that is a fantastic idea, especially, right, if this is a biotic ocean. That's something that we definitely need to do. And then the other thing that people have been talking quite a bit about, what was that last one? Oh, ramen, UV ramen. People really like UV ramen, and it looks like Michael Malaska has a UV ramen that we can use.
That's great. Yeah, you definitely, if you go to the effort to get down there, you want to be able to make the discoveries that you're looking forward to. So it's great to hear you're planning well.